see haloalkanes are nucleophile terms. So in this nucleophiles, what I am teaching this um, part 11 and part 12 is based on only the basic things you should know. Only then we can apply, and only then you can understand why we are using these solvents, why we are using nucleophiles are very weak or strong, how they are attacking, why they are called as a protic solvent or a aprotic solvent and all. You just learn this one. Nucleophiles, just once you just go through. Nucleophiles are species with donating the pair of electron is called nucleophiles. It will have the ability to donate electrons. So ability to donate electron will increase as it becomes more electron rich. So when the electron rich center will be attacked only, will the have the possibility to donate the electrons. So decrease as decreases, it becomes a more electron poor. So it should increases. It should not decreases, right? So now we'll see electron density increases, so that nucleophilicity also increases. So electron density increases, nucleophilicity also will be increases. So what nucleophilicity is nothing but basicity. So nucleophilicity depends upon the factors including charge, electronegativity, solvent, and steric entrance. These four factors will be affect the nucleophilicity. So the nucleophiles we have neutral nucleophile and negatively charged nucleophile. For example, OH minus is the negatively charged nucleophile. So oxygen in OH minus is negative. And but the same oxygen in water, it is called as a neutral nucleophile. Neutral nucleophile examples H2O, NH3, or NH2, R2NH, primary amine, secondary amine, tertiary amine, R3N, alcohol ROH, acid RCOH, thioalcohol RSH, and this is phosphine, trialkyl phosphine. So negatively charged nucleophiles all carries negative sign, RO minus, or NH2 minus, RNH minus, R2N minus, HS minus, RS minus, RSE minus, the selenium, this is one of the metal, and Cl minus, Br minus, I minus, F minus, Cn minus, OH minus, RCOO minus, or negatively charged nucleophiles. Negatively charged reactive atom is better than the nucleophile containing the reactive atom in neutral nucleophile. So negatively charged nucleophiles are better than neutral nucleophiles. So OH minus is a negatively charged and H2O is a neutral. So both contains oxygen. So OH minus is the better nucleophile. So OH minus is better than the H2O. And same way, nitrogen in NH2 is a negatively charged and nitrogen in ammonia is a neutral. So NH2 minus is greater than NH3. So factors affecting the good nucleophiles, I said of 4 factors: charge, electronegativity value, and using solvent, and using steric entrance. Using solvent only, we are going to see in a SN2 mechanism and SN1 mechanism. First, you see, let us one by one. Charge. These are things you learn properly. You can write all the competitive exam. Don't think always a NEET exam, JEE exam. Not only that, in the world, we are a lot of groups are there, competitive exams are there. You be attend all the exams by applying all the knowledge. So for that, you apply, read everything. Extra points whenever you read only, we can answer the competitive exam. So for a charges, OH minus is better than the H2O because this is negatively charged nucleophile. It is a neutral nucleophile. And charge is very, very important. Next thing is electronegativity. I told you the electronegativity that from here left to right, the electronegativity character is increasing. Fluorine 4.0, chlorine 3.0, bromine 2.8, and iodine only 2.5. But when you come from here, lithium 1.0, beryllium 1.5, boron 2, and carbon 2.5, and nitrogen 3.0, oxygen 3.5, and fluorine 4.0. So from here it comes, it increases. From top to bottom, it is decreases. From left to right, increases. Top to bottom, decreases. So electronegativity value in periodic table across a row, nucleophilicity follows the basicity. Nucleophilicity increases from left to right, that increases. And with the decreasing in the electronegativity, just you see this. Here right to left you are coming, right to left, it is nucleophilicity increases because as the electronegativity value decreases, nucleophilicity increases. So here hydrogen 2.1, lithium 1.0, 0.5, 0.5 difference only. Easily you can remember. See, lithium first group, second group, third group, fourth group, fifth group, sixth group, seventh group. So here 1.0, 1.5, boron 2.0, carbon 2.5, hydrogen 3.0, oxygen 3.5, fluorine 4.0. These are the electronegativity value from right to left, that nucleophilicity increases as the electronegativity value decreases. So N in NH2 minus more nucleophilicity than O in OH minus, because nucleophilicity for a nitrogen is less than the oxygen. So more nucleophilicity is a NH2 than oxygen of OH minus. So here carbon, nitrogen, oxygen, fluorine 4.0, 3.5, 3.0, 3.5. So it is more, less electronegative, more of nucleophilicity. So CH2 minus is greater than, NH2 minus is greater than, HO minus is greater than F minus, because here it is one lone pair, here two lone pair, three lone pair, and it is a four lone pair, it is a burst. NH3 is greater than, H2 is greater than HF. Reason, nucleophilicity is a domination of electron pair. I mean, donating the electron pair is the main thing. The electron pairing alone, it is dominating, whether it is giving capacity or it can not capable of giving capacity. That is called as a lone pair of electrons is a donation by the nucleophilicity. If it is a less electronegative atom, less tightly held, so easily it can donate. That is the main thing of having less electronegative atom having the more nucleophilicity, because they are very tightly held, easily they can donate. So donation is a very, very important thing. So next thing is solvent. Now we are coming to the first what we are seeing, that SN2 mechanism and SN1 reaction now. So that we are using what type of solvent to be used. So here a protic, aprotic, and this is a polar aprotic, and this is a polar protic. PP we should here we should use a PA. PA is called polar aprotic. This is called polar protic. Let us see, there's a polar solvents with the different charges. Non-polar solvents are having not difference. They are both positive or both negative. Here one positive, one negative is called polar. This is non-polar. Example, benzene, chlorohexane, and N-hexane. These are similar. So it is called non-polar. Polar means water, H plus and OH minus. We can say very good example for polar solvent. In polar solvent, we have two types. One is a polar protic solvent, that is called PP solvent. Polar aprotic solvent, it is called PA solvent. Polar protic solvent, polar aprotic solvent. Now we will see definition of polar protic solvents. Donate H plus. Polar aprotic means it is not donating the H plus, because A means in Greek not. So what A, whenever A comes, for example, atom only you are saying ATOM, atom. A means what? Not cut. Atom means cut, A means not. So what? Atoms cannot be cut. So it is indivisible particle. So what atom means? Not it is indivisible particles, not cut down. So like that A comes, it is called not. So it cannot having the H plus. So polar protic is donating the H plus. Polar aprotic means donating, cannot donate the H plus. So no crowded center will be in a polar protic. There are a crowded center in a polar aprotic. What is crowded? And let us see this. Polar protic can donate H plus, more solvation, no crowded. But polar aprotic cannot donate H plus, less solvation, have a crowded positive center. For example, polar protic water, methyl alcohol. But polar aprotic crowded shape. Here one CH3 and here CH3. So this is called crowded center. So acetone is a good example. In this example of CO is not containing any hydrogen to donate. But here this oxygen contains a hydrogen to donate. So it is called donating a hydrogen is called polar protic. Not donating hydrogen is called as a polar aprotic. Polar protic solvent effect. Polar protic solvent interact with the negatively charged nucleophiles. So if we use a polar protic solvent, Negatively charged nucleophile decreases the electron density because polar protic is giving hydrogen. So hydrogen will take the electron, then decrease the electron density in a nucleophile. But nucleophile character means always donating the electron. So the donation of the electron will be decreases because by adding the hydrogen content. So the decrease the electron density will make the H bond if we use a polar protic as a solvent. So solvation is weakens the nucleophilicity. So the solvation decreases the nucleophilicity. Or for example, this is the ROH if we use. So this is bond forming the hydrogen bond. So solubility will be takes place. So small anions are more tightly solvated than the larger anions. What do you mean by smaller anion? For example, fluoride ion is more heavily solvated than the larger iodide ion. So I minus is stronger and F minus is weak. So fluoride anion will be a weaker nucleophile than the iodide anion. So polar protic solvent weakens the nucleophilicity. Polar aprotic, let us see. Here acetone I said, here no hydrogen on a CO bond. Then here instead of here it is a CO. I mean here it is we have taken as a SO. So what this is called dimethyl sulfoxide. Dimethyl sulfoxide. 2-methyl sulfur with the oxygen is called sulfoxide. Instead of carbon, I have substituted sulfur, so it is called sulfoxide. So dimethyl sulfoxide also it is a crowded one. Here of formamide. HCONH2 is called formamide. This is basic formula. HC double bond O NH2 is a formamide, or we can say HCONH2. In this NH2 2 hydrogen, we have substituted 2 methyl group. So this is called dimethyl formamide. Dimethyl formamide also one of the example form polar aprotic, and this is called acetamide CH3CONH2. In this CH3CONH2 C double bond O NH2. In this acetamide, instead of 2 hydrogen 2 methyl is substituted, so it is called dimethyl acetamide. So it is called as a DMA is a dimethyl acetamide, DMF is a dimethyl formamide, DMO is a dimethyl sulfoxide. It is called acetone. These are the example for polar aprotic solvents. So polar aprotic solvents are crowded positive center. They do not solvate the nucleophile. Not solvate means not taking this nucleophile electron. So faster the reaction is SN2 reaction increase when they carried out polar aprotic solvent. It is the best solvent is polar aprotic for a SN2 reaction. Polar aprotic solvent under the periodic table nucleophilicity does not follow the basicity in a moving up and down in a particular group, but it is in a left to right or right to left. You see, right to left the electronegativity value decreases means nucleophilicity increases, basicity increases, but just opposite in a group. So basicity decreases, nucleophilicity increases. When basicity increases, nucleophilicity decreases. For example, top to bottom, fluorine small, chlorine, bromine, iodine more electronegative 4.0, 3.0, 2.8, 2.5. So size increases, basicity decreases, but nucleophilicity increases from top to bottom. Just opposite in a period. Polar aprotic is the example of dimethyl sulfoxide, dimethyl formamide, and dimethyl acetamide. A. So what the acetone is another example. More on basic nucleophile is F minus for a polar aprotic. For a polar protic, it is just opposite. I minus is the best one. So here undergo that apart from this, here the metal. So pH is greater than NH3, and selenium hydride is greater than hydrogen sulfide is greater than water. So size increases, basicity decreases, nucleophilicity increases. So this is the just for your basic concept of have an idea about a protic and polar protic and polar aprotic and what is nucleophilicity in a period and a group. Thanks for watching.